Hello, and welcome back to Passing College Level Chemistry. This is part 2 to the Density Explained with Practice Problems video. In this video, we'll be looking at some density challenge problems. These are more likely, if you're in the college level, to be seen on a quiz or an exam. And so we're going to work through these together. Also, I wrote both of these questions. I'm a tutor as well as a student, and part of my job is to come up with problems, and so these are both problems that I have written and used in tutoring sessions, so that's why there's no textbook number. Alright, so we're going to get started. We're told that we have an empty flask that weighs a mass. After filling the flask with a volume of a liquid, the flask weighs a certain weight. And we're asked to find the density in grams per milliliter. So I'm going to break this down. Instead of doing a given in a find like I did in the previous video, we can still do that. I'm just going to use pictures and kind of use that as a way to see what we're working with. So flask, beaker, I'm going to call this a flask. We have an empty one. I'm just going to say empty. And this has a mass of 168.9 grams. It has no volume in it yet. And then we have a volume of that same flask that's filled in this. So I'm just going to kind of draw a liquid in there. So this will be with the liquid. I'm just going to abbreviate it. The mass of that, we're told, weighs 182.4 grams, and the volume of liquid that's been added is 7.89 milliliters. This is something that we might do in a lab. In lab, what you might do or see is you'll take the mass of an empty beaker, and then you'll take the mass of the beaker with whatever you've added to it. It could be a liquid or maybe a solid if you're making a solution or something. And the reason that we take that empty mass is because we can actually subtract the mass of that empty container from the mass of the container with the liquid. And for reasons like we'll see soon, eventually, is like concentration. We can actually calculate that. Mass is a huge thing. Understanding these concepts, these fundamental concepts, will help us. But here we're going to find our density. We want to know what it is in units of grams per milliliter. So we're off to a good start. Everything has the same units. The way that we can find this, I'm going to switch colors. If we find the mass of the liquid, because right now we have mass of flask plus liquid. I'm going to abbreviate that. Mass of flask plus the liquid. That's going to be this right here. We can subtract the mass of the flask. This would be just mass of the flask. And that will give us the mass of the liquid. Hopefully you see that if I drew another little diagram. Here's my liquid. If I wanted to find just the mass of that liquid, if I knew what the mass of this container was, I could subtract it and subtract or erase. Doing so would just give me the liquid right here. So hopefully you can see that taking away that mass of the flask will give us the mass of the liquid. We don't really have a change in volume. We're going just from 0 to 7.89. But another way that you might see density written is density equals the change in mass divided by the change in volume. I'm just going to put these in absolute bars. We can never have a negative change in mass unless we're actually subtracting it. And in these types of examples, we don't do that. if you see this symbol, this means change. So really this is just saying density is the change in mass divided by the change in volume. And in general chemistry, in all chemistry, usually a delta is related to a final minus initial state. So delta V would mean we're taking that final volume and subtracting the initial volume, or delta mass is the final mass minus the initial mass. So using the final and initial, we could also say this is my initial state, an empty beaker or an empty flask, and this is my final state with the liquid. And we're just trying to find the density of that liquid. I'm going to switch back to my other color. So doing so, I need to find, there's an obvious change in mass. I'm going to find that delta M. And I'm going to take that final mass with the liquid, and I'm going to subtract that initial mass, the mass of the empty flask. So this and this, or you could do final minus initial. When I do the math for that, I get a mass of 13.5 grams, and that is to the correct number of significant figures. If I look at my change in volume, my final volume is 7.89 milliliters. My initial volume is 0.00 milliliters. My change in volume is 7.89 milliliters. Now I know both of those. I can just plug that into my density equation. Go ahead and put 10.5 grams divided by 7.89 milliliters. My density of this liquid comes out to be 1.71 grams per milliliter. That is the answer to that problem. That would be like a quiz question. Alright, so this next problem is a little harder than the previous problem. We're kind of upping it a notch. This is more of a problem I could see being on an exam. So hopefully this gives you a good idea. We are going to start with what we're given, and then go into what we're asked to find. As we read this problem, I'm going to also just annotate it. So it says a 747 jet can carry up to approximately 238,840 liters of fuel. That's as full as it can get. So I'm going to go ahead and say this is my volume of a full tank of fuel. During a trip, the jet burns 189,000 liters of that fuel. So this would be volume, we'll say burned. If the density of the fuel is 769 kilograms per cubic meter, how many kilograms of fuel are left in the jet? So ask for kilograms that are left. A couple key pieces of information in this. So I'm going to go ahead and just copy that down. I'm writing the density out in a fraction form that second way, just to show that it's a conversion factor between kilograms and meters cubed. We can flip that depending on what we need to do with the problem. Then we're asked to find what is the mass? Kilogram refers to a mass. What's the mass left? Now we have a couple words here. We have full, burned, and left. I'm going to draw just a rough picture. I'm not an artist, but I like diagrams and pictures just to help me follow along. We can say this rectangle is the tank. So it can be full. That's how it would look if it were full. However, we've burned just over half of that tank's capacity. So I'll say maybe about that much is how much we have burned. This white box, and I'm actually going to fill it in with another color. We'll go ahead with yellow. That yellow box is how much is left in the tank. And if we think about this diagram, we can talk in terms of volume or we could talk in terms of mass. But the way that I'm going to do it is I'm going to talk in terms of volume because we have more information about volume given to us than we do mass. We could go through the math and convert each of these volumes into masses using the density. But I'm going to show you a simpler, faster way to solve this problem than going through all of the nitty-gritty steps. So what I'm going to have us do is write an equation for this tank. We can say the full volume, the fullest capacity that we could have this tank at is equal to the volume burned plus the volume that's left. I can rearrange this, solving for the volume that's left, by subtracting the volume burned from both sides. I'm just rewriting it with having what I'm solving for on the left. Doing that, I'm going to kind of show you my thought process here. If we have a volume, if we find the volume that's left, we can find the mass that's left using the density. So using these two equations that I've starred, and I'll go ahead and highlight those as well, using these two equations or thought processes will help us solve this problem. So I'm going to start with that top one. The volume left, 238,840 liters minus 189,000 liters. If we punch this in a calculator and rounding to the proper number of sig figs, you should get 49,840 liters. That is our volume left. I can now do a series of conversions to get to kilograms left. And the way that we're going to do that is go from liters, this should look a little familiar, you're going to see this a lot, liters to milliliters, to cubic centimeters, to cubic meters, to kilograms. Liters to milliliters is a unit conversion, milliliters to centimeters cubed is a unit conversion, cubic centimeter to cubic meters is a unit conversion, cubic meters to kilograms, we're using density. So all of these are known, we're using density for that last one. We'll go through that. So using this volume, rewriting it down here so I have more room, I'm going to convert from liters to milliliters. To do that, I can put my milliliters on the top, my liters on the bottom. My liters will cancel. Next, I can convert from milliliters to centimeters cubed. That's just 1 to 1. Next, I can convert from cubic centimeters to cubic meters. That might be a little tricky if you're ever dealing with an area or a volume. Usually these are all length. We know that there are 100 centimeters in 1 meter. That is a length. And I write length as that little curvy L. A volume is just length cubed. So I can take the 100 centimeters, I'm going to put that in parentheses and my 1 meter in parentheses, and I'm going to raise it to the third power on both sides. That's cubing my length. That gives me a volume. When we do that, the 3 distributes to both the 100 and the centimeters, as well as the 1 and the meters. And if I rewrote that, that would go to 100 cubed, centimeters cubed, 1 cubed is still 1. If you're thinking about it, it's just 1 times 1 times 1. It's going to be 1. And then meters cubed. 100 cubed is 1,000,000. But just to keep this kind of nice and clean, I'm going to, and to avoid writing a bunch of zeros, I'm just going to put 100 cubed cubic centimeters and then 1 meter cubed. Now those will cancel out. And I can do my last conversion, which is going to be converting from meters cubed to kilograms. And that's where I'm going to use my density. I can use that as a conversion factor. And I can write it just as it is. I won't have to flip it or anything, because if I write it this way, it allows me to cancel out those cubic meters. And now I'm just going to look at my setup, make sure everything is put in correctly. It looks good to me. If I go ahead and put that in a calculator, and rounding to 3 significant figures, I get 3.83 times 10 to the 4th kilograms. I wrote it in scientific notation because if I wrote it out as this, it's hard to tell how many significant figures there are, and this is clearly telling the reader that there are 3 significant figures. It's also a large number, so it's more common to write it in scientific notation. So this is my final answer. That's a lot of fuel that's left over. Again, we could have gone through it the long way. The long way would have just been converting each volume to a mass. And if that's what you did, that's great because you're thinking when you're working. Then you would find the mass that's left. And that's another way you could do it. It's just a little more, a few more extra steps. This just saves you some time by doing this step at the beginning. But I hope that this video helped you. Again, if you have any questions, please feel free to leave a comment. Thank you for watching.